Alright, here we go. Chapter 2, Limits and Continuity. We are in 2.1, Rates of Change and Limits. Your objectives for this lesson are to find average and instantaneous speeds and to define limit. To find average speed, all you need to do is divide the distance covered by the elapsed time. So speed equals distance over time. And your unit is always that length, so distance, divided by unit of time, so distance divided by time. For instance, miles per hour is something that you have seen many times before. Our first example. A rock breaks loose from the top of a tall cliff. What is its average speed during the first 2 seconds of fall? This problem seems very difficult right now because we only have one number, 2, and I'm asking you to find the speed. But it's really not as hard as it seems. We're going to use this formula to help us solve the problem, that is y equals 16 t squared feet. And this formula comes from physics. So this is the distance that an object in free fall will fall when air resistance does not matter. The 16 is half of the gravitational constant, 32, when you're using feet instead of meters. So again, you would see that in a physics class. So we've already established that speed is change in distance over change in time. Those triangles are delta. Remember, delta means change. So our distance is y, so delta y, over time is t, so delta t. And let's use this equation now, substitute, so we only have one variable. 16, our endpoint is at 2, so plug in that 2, squared, minus, we started at t equals 0, so plug in a 0 here, all over, change in time is 2, stop point, minus 0, your start point. Now we're going to simplify. So we have 16 times 4, which is 64, minus, this is going to be 0, because anything times 0 is 0, over 2. Minus 0 goes away, and 64 over 2 is simply 32. And our unit, remember we had feet for distance and seconds for our time. So our average speed is 32 feet per second. Example 2. Find the speed of the rock from example 1 at the instant t equals 2. This is a little bit more challenging than the first example, mostly because if we try to use delta y divided by delta t, we're looking at an instant. So in an instant there is no change in time, so we really have delta y over 0, which you cannot do. You cannot and will not divide by 0. So we need a different approach. Let's try calculating this based on the time 2 plus h, which is a time slightly later than t equals 2. And when I say slightly, I mean the very, very least amount of time, or than t equals 2. So you're adding the smallest possible increment that you can to 2. Therefore, we can just plug this in like we were doing before. So we're going to have this end time, plug in the 2 plus h, minus our start time was at t equals 2. We have 2 plus h minus 2 in the denominator, which simplifies to just be an h because those 2's are going to cancel out. So cleaning this up just a little bit. Okay. And from here, you could plug this right into your calculator. Of course, remember your parentheses on top, and you're using x's instead of h. And we want to look at the table feature for this problem. So you're going to go here, plug into the table. Sorry. Alright, so we can do, let's do table set, and I want to input my own values. So let's go to the table, and you see it's completely blank. That is what I want. And let's see what happens when I plug in 1 for x. So if it's 1 second at t equals 3, really, then our y, our speed, is 80. So at h is 1, you're going to have 80 for your speed. Let's try something a little bit smaller because 1 is pretty big. Okay, so if I plug in 0.1, that is a tenth of a second, we get 65.6 for the speed, 65.6 feet per second. That is a huge drop down. So I want to see what happens when I continue to plug in smaller values. So I'm just going to add in 1 0 in front of that 1, so 0.01. And I can see y getting smaller. So let's put in a few more of these. I'm just going to keep putting zeros in front of the 1. So this was four zeros in front of it. So 0.00001, and I got 64 there. If I put 5 zeros in front, we get 64 again. So it looks like it's not getting any smaller than that. It looks like then I'm going to guess that at t equals 2, my speed is approximately 64 feet per second. So here we made a table. And we're going to say delta y over delta t is 64 feet per second. Okay. And we can actually confirm this algebraically. So that was kind of a guess, but we want to know for sure. So we're going to work out this equation and simplify it. So we have delta y over delta t equals 16 2 plus h squared minus 16 times 2 squared over, we said that simplified to an h. Okay, so you need to expand this binomial out if you do not know how a perfect square multiplies. If you do, then use your shortcut. So we're going to have 4 plus 4h plus h squared minus 16 times 4 is 64 over h. Distribute your 16, so we have 64 plus 64h plus 16h squared minus 64 over h. These 64's cancel, and you see the common factor of an h here, so those all cancel. And we are left with 64 plus 16h. But h, we don't really want to see an h there. We would like a nice number. What you need to do is plug in a 0 for h. The reason for that is, remember, h is the smallest increment of time possible, greater than 2, and the smallest number to add to 2 would be 0. That would be the smallest change. So if we have 64 plus 16 times 0, we really just have 64 feet per second, which is what we hypothesized that time would be. Or not time, sorry, that speed would be. So that is pretty good. We did a good job with the table and guessing there.